Download this code from codegive.com, link in the description below. OK, let's embark on a detailed journey into the Java Security Manager, exploring its history, purpose, mechanisms, and how to use it effectively. I'll provide explanations and code examples to make the concepts clear. The backstory: why a security manager? In the early days of Java, the concept of applets was central. Applets were small Java programs embedded within web pages, downloaded to a user's browser, and executed locally. This presented a significant security challenge. Untrusted code. Users were downloading code from unknown sources, the internet. How could they be sure that this code wouldn't harm their system? What if it tried to read local files, modify system settings, or launch attacks? Limited trust. The initial trust model was based on the idea of sandboxing. Applets were supposed to be restricted in what they could do, preventing them from causing harm. Early Java's vulnerabilities. Early versions of the Java Virtual Machine, JVM, had security vulnerabilities. Exploitable bugs could allow malicious applets to escape the sandbox. The Java Security Manager was designed to address these problems. It was introduced in Java 1.0 as a core component of the Java security architecture. Its primary purpose was to control the actions that Java code could perform. It acts as a central gatekeeper. 2. The Security Manager's role. The Security Manager provides a mechanism for access control, determining whether a piece of code has permission to perform a specific operation, example reading a file, opening a network connection, accessing system properties. Privilege separation, allowing some code, example trusted system code, to have more privileges than other code, example downloaded applets. Security policy enforcement, defining the rules that govern which code can do what. These rules are typically defined in a security policy file. 3. How the Security Manager works, a deep dive. 1. The Security Manager class. The Java.lang. Security Manager class is the heart of the system. It's an abstract class that defines the core methods for checking permissions. The JVM has a single, globally accessible Security Manager instance, or null, if no Security Manager is installed. You can subclass Security Manager to create a custom Security Manager, although this is less common these days. 2. The check XXX methods. The Security Manager class provides a large number of check XXX methods. These methods are invoked by Java libraries and the JVM itself whenever a potentially sensitive operation is about to be performed. Examples: check read, string file, check write, string file, check connect, string host, import, check permission, permission perm. These methods throw a security exception if the current code does not have the necessary permission. 3. The access controller class. The Java.security.access controller class provides the check permission method, which is the central entry point for permission checking. The access controller walks up the call stack, the chain of methods that led to the current operation, to determine the permissions of all the code in the call stack. The access controller considers the protection domains of the classes involved. 4. Protection domains. A protection domain represents a set of classes that have been granted a specific set of permissions. Every class loaded by the JVM is associated with a protection domain. A protection domain is essentially a set of code signing certificates and a set of permissions. If code is signed with a specific certificate and its permission set is granted, the protection domain determines what the code can do. 5 Permissions asterisk. Asterisk permissions are represented by classes derived from java.security.permission. Asterisk Java defines a hierarchy of permissions, such as java.io.file permission, java.net.socket permission, java.security.all permission, etc. Asterisk permissions can be granted to code based on its origin, example a specific codebase URL, or based on the signer of the code, if the code is signed with a certificate. 6. The security policy file asterisk. Asterisk The security policy file is a text file that defines the permissions that are granted to different code bases and signers. Asterisk The default policy file is usually located in java.home/lib/security/java.policy. Asterisk You can specify a different policy file using the java.security.policy JVM argument. 7. How it all works together asterisk. A piece of code attempts to perform a sensitive operation, example opening a file. B. The Java library or the JVM calls a checkxxx method on the security manager. C. The security manager usually delegates to the access controller.checkPermission method. D. The access controller examines the call stack and the protection domains of the classes in the call stack. E. The access controller consults the security policy file to determine whether the code has the necessary permission. F. If the code has permission, the operation proceeds. If not, a security exception is thrown. 4. Code examples. Let's illustrate with some practical examples. Example 1, installing and testing the security manager. To run this example, you'll likely need to create a file named test.txt in the same directory as your Java program. 1. Compile *javac security manager example.java. 2. Run without a security policy *java security manager example. This will likely throw a security exception because the default policy doesn't grant file read permission to the current directory. 3. Create a security policy create a file named my.policy in the same directory as your class file with the following content. This policy grants read permission to test.txt in the directory where you run the program. $user.dir is a system property that expands to the current working directory. $/ is a platform-independent file separator. 4. Run with the security policy java.security.policy equals my.policy security manager example. This should now succeed in reading the file. Explanation We install a default security manager if one isn't already present. We attempt to read a file. If the security manager is active, it will check if we have permission. Without a policy file that grants permission, a security exception will be thrown. With the policy file, we grant read permission to the specified file, and the program runs successfully. Example 2, using permissions programmatically. To run this example, you will need to create a file named another_test.txt in the same directory as the Java program. 1. Compile *javac permission example.java. 2. Run without a security policy *java permission example. This will throw a security exception, as privileged action does not automatically grant permissions. We need to set a permission in the security policy file. 3. Create a security policy create a file named my2.policy in the same directory as your class file with the following content. 4. Run with the security policy java.security.policy equals my2.policy permission example. This should succeed because we are granting the read permission in the policy file. Explanation access controller.doPrivileged allows code with higher privileges to perform actions on behalf of code with lower privileges. In this example, even though the main method may not have direct access to the file another_test.txt, the code within the privileged action can be granted the file permission to read the file if it's present in the policy file. The access control context is provided with an empty protection domain, effectively removing the caller's permission set during the execution of the privileged action, and relying solely on policy-based permissions. V. The security policy file, syntax and examples. The security policy file uses a simple syntax. Here's a breakdown. *grant* starts a grant entry, defining a set of permissions for code matching the specified criteria. *signed by *, optional, specifies the aliases of the certificates used to sign the code. You can specify multiple signers, separated by commas. *codebase*, optional, specifies the URL of the code, example a directory or a jar file. You can use the special value * to match any code base. *permission * declares a permission. *permission _class_name, the fully qualified name of the permission class, example java.io.file permission. *target _name, the target of the permission, example a file name or a URL. *action, optional, the action allowed for the permission, example read, write, connect. Example policy file entries *. Key policy file considerations *. Case sensitivity * policy file syntax is case sensitive. *variables * you can use system properties, like $user.home, in policy files. *wildcards the *wildcard character can be used in file paths and URLs. Multiple entries you can have multiple grant entries in a single policy file. The permissions granted to a piece of code are the union of all matching entries. 6. When and why use the security manager? Applets. Historically, as mentioned earlier, applets were the primary reason for the security manager's existence. With the decline of applets, this use case has become less relevant. Applications with plugins if you have an application that loads plugins from untrusted sources, the security manager can help to sandbox those plugins and prevent them from harming your application or the user's system. Multi-tenant environments in environments where multiple untrusted applications run within the same JVM, the security manager can be used to isolate them and prevent them from interfering with each other. Defense in depth even if you don't have explicitly untrusted code, the security manager can provide an extra layer of defense against security vulnerabilities. If a vulnerability is exploited, the security manager might be able to prevent the exploit from causing significant harm. When not to use the security manager, and alternatives. Simple applications for simple, single-user applications where all the code is trusted, the security manager is usually unnecessary overhead. Modern alternatives, containers, isolation, and secure coding practices containers, Docker, etc. Containers provide a much stronger form of isolation than the security manager. Each application runs in its own isolated environment. Virtual machines similar to containers, but provide complete hardware virtualization. Secure coding practices the most effective defense against security vulnerabilities is to write secure code in the first place. This includes using secure libraries, validating input, and avoiding common security pitfalls. Modular Java 9 plus the Java Platform Module System, JPMS, provides a way to define clear boundaries between modules, limiting the visibility of classes and packages. While not a security mechanism in itself, it can help to reduce the attack surface of an application. 7. Caveats and challenges. Complexity. Setting up and configuring the security manager can be complex, especially if you have a large and complex application. Performance overhead. Enabling the security manager adds a performance overhead to the JVM, as every sensitive operation must be checked. Compatibility issues. Some third-party libraries may not be fully compatible with the security manager. They might make assumptions about privileges that are not valid when the security manager is enabled. Maintaining policy files. Keeping the security policy file up to date can be challenging, as your application evolves and new libraries are added. 8. Conclusion. The Java Security Manager was a pioneering security mechanism in the early days of Java. It provided a way to sandbox untrusted code and prevent it from harming the user's system. However, with the rise of containers, virtual machines, and modular Java, the security manager has become less essential for many applications. Modern security best practices emphasize writing secure code and using strong isolation techniques. While the security manager remains a part of the Java platform, it's important to carefully consider whether it's the right tool for your specific needs.